We're going to make a brief digression here in our consideration of improper or infinite integrals. And this is to confront some of the, quite honestly, well-placed suspicions students have about these. If you are happy with what we're doing, you can feel free to skip this video. This is for the doubters or disbelievers among you. When confronted with this idea of the area underneath a graph, but going out to infinity, there's two common responses. One is to think that because we're going out to infinity, look at this size here. The side of this area is infinite, and so I don't care what the top is doing, the area must be infinite as well. How can it be anything else, right? This side's infinitely long, the area must be infinite. Completely reasonable thought. We will hopefully be able to convince you otherwise by looking at an example. An opposite reaction, though, that some people have is to say, well, look at this graph. As long as this graph goes down towards zero, then it doesn't matter how far we go out, the graph is going to zero, so the area must get finite. It must stop growing at some point. And I wish it was that simple too, but we can also show an example where even though the graph does get smaller and smaller, the area keeps growing larger and larger and goes off to infinity. So fundamentally what we're dealing with here is the sum of a function and times delta x, and the sum of the delta x's, that's going off to infinity because we're going in one side and one dimension out to infinity. But the f of x part, the function, is approaching zero. We're approaching infinity and approaching zero, so we have two competing interests going on, and we don't know, without knowing the details of the function, what's actually going to happen. It's unfortunately never going to be as simple as, oh, it's always finite. Sorry, over here, it's always finite, or over here, it must be infinite. If it was that easy, we wouldn't be spending sort of half a unit on this. So let's take a look at these two arguments and try to find examples that contradict the simple, intuitive reasoning behind both of those. Intuitive but fishy, because zeros and infinities are very, very, very slippery things. So let's consider the infinity case. So the case where we say the graph goes out to infinity, therefore the area underneath that graph must be infinitely large. Here's a nice mental game you can play. Let's take two blocks, each that are 1 square unit. If those two blocks are put side by side, I think we'll all agree they both still have 2 square units of area. What we can do next is then keep the first block and cut the second block in half. So we have 1 and a half and a half. Still area 2. That's the key thing. Then we can cut this third block in half, and we'll have a block that's 1, the next block that's a half, and the next block that's a quarter. Area? Oh, we better add a block at the end there. Another quarter. Area? Still 2. Well, I think you can see where this is going now. A quarter and then 2/8. So 1/8 and 1/8. Area? Still 2. If we keep that progression going, 1, a half, a quarter, an eighth, a 16th, a 32nd, a 64th, a 1/28th, blah, 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 we can always do that one more time. This is math. This isn't real pieces of paper or anything. And when we do that, what's the area going to be in the limit as we keep doing that operation? The area has to be 2 every time. All we're doing is subdividing what we already had, but the x interval would be infinite. So even though we take the limit and we keep doing this over and over again, the area is always 2, so finite, even though the x interval is infinite. So if you can imagine that working its way out, that's how we can get an integral that's finite, even though we have an infinitely long x interval. Because you can imagine this is upper bound here. If we had a graph that went through these guys here, like so, the area underneath that graph would be smaller than the area in the rectangles or the squares. And so, while the area in the squares is 2, the area in the graph is less than 2, definitely finite. So we can make an argument about continuous functions just as well as we can using the simpler blocks. So that should be some argument if you're thinking, well, no, this side here is infinitely large. The area above it has to be infinitely large as well. Well, not as long as these things get small fast enough. Now we're going to look at the contrary side of that and see what we can see. So with that other argument, you might say, well, maybe the infinity doesn't matter. Maybe anything, as long as it goes down towards 0, maybe this area has to be finite. Fair case. Okay. Let's take a look at blocks again, though, because blocks are easier than functions. And what we're going to do is have a block of height 1, and then a block of height of a half, block of height of a third, then a quarter, and then a fifth, and then a sixth, and then a seventh, and so on. And let's go down to 1/8 for now. They should look narrower and narrower. I apologize. So this argument, what are we trying to say? Well, these are going to 0. These areas for each individual block are definitely getting smaller and smaller, and these values are approaching 0. So is the area when we add them all up finite? Well, maybe. Oh, well, actually we can show pretty quickly that it isn't, because we can group these things. I've got 1 here. I've got a half. So the area here is what we're looking at. And what I'm going to do is group the third and the quarter together. A third and a quarter, well, a third is bigger than a quarter, so these two things are bigger than another half. So the area is actually at least a half when we group these two things here together. A third and a quarter is bigger than two quarters. Okay, well that doesn't help too much, but then we can look at these next 4. An eighth, something bigger than an eighth, something bigger than an eighth. 4 things that are an eighth or bigger, that's going to be bigger than 4/8, better known as 1/2. And so my area up to here is a 1 plus a half plus a half plus a half at least. It's actually bigger than that. And then what can you imagine as we go on further down to 1/16? This had 4 terms, this would be 8 terms here. If we gather those next 8 terms, whatever we get is going to be bigger than 8/16, also known as a half. And so we can see, because of this infinite progression, even though the terms are getting smaller and smaller, we can have 1 plus a half 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 plus a half. It takes more and more terms, but we have an infinite number of them. So at the end of the day, this whole sum, the area, must go to infinity as well as we add terms. It's not going to stay at 2 like the previous example did. We're always going to get bigger. And if you say, well, the area is 100 then, well, I just keep adding terms until I get past 100. I can prove that we get past any value, any finite area that you care to think of as a final answer, just by adding more terms. So what do you learn from this? Even though this function gets smaller, and again, we could do this as a continuous function, just going through the corners here, even as the function approaches 0, by having an infinite number of terms, it's possible, not guaranteed, but possible to have an infinitely large area. So through these 2 examples, this one here where the area is infinite, and this one here where the area was always finite, but just broken down over an infinitely long x dimension, we can get both cases. And again, it comes down to the tension between this 0, the function going towards 0, and the infinity part, which is the length of the x interval, and how those two interplay. That's going to be what determines whether we get a finite or an infinite integral when we start looking at the continuous versions of these.